Good morning, all of you. Today I'll be talking about plastic analysis of materials. Like we'll be talking about beams, different kind of beams, how the plastic analysis occurs in that type of beams. Basically, I would like to start with why plastic analysis, why we needed that. Because plastic analysis plastic behavior of a structure starts when the elastic limits ends. And what is the elastic limit is said to be that limit of a material like steel, any kind of material, it could be cork, any kind of. So elastic limits ends at point which when stress is not proportional to strain. What I'm trying to tell is that when stress is proportional to strain, that time is known as elastic limit. After that, the material get yielded and the plastic nature of material starts. And in plastic deformation, the ultimate collapse load occurs. Basically, in elastic behavior of a material, we study at the point till the point of yielding, and in plastic deformation we study till the collapse load. What are the safe loads, and what are the concept of designs based upon the ultimate load design? It is basically, yes, designing with plastic analysis is economical and optimum use, and the material is used for at the optimum level. Because in elastic analysis, only at yielding point we stop. We say that it is a end. The crack starts, our material failed. But in plastic analysis, we study till the collapse load, the ultimate usage of material is captured. Now, there are two type of materials. First, we'll talking about elastic and elastic perfectly plastic. Basically, uh, there's the elastic limit point here till sigma y. This is called elastic limit in first diagram, and in second diagram there is a perfectly plastic. This material is perfectly plastic type material where the linear line, parallel line, the x-axis is shown, mean that is strain, parallel line to strain is shown, means this is perfectly plastic. And we do unloading, when it will come back to its original state. Okay, this is the stress strain curve for the mild steel, very famous stress strain curve. In this, at from O to A, it is regarded as the elastic limit. From O to A, at A the steel get yielded. From A to, there's a two yield point in this case, A to B, lower yield point. Then from B to C, the basically the plastic plateau is regarded, where the plastic range, then there is no increase in stress and only strain value is increasing. Then the strain hardening and the strain softening comes, and then ultimate collapse happens. Now, this is the idealized stress strain curve in plastic theory. But we idealize means basically what we want. We want stress at point of yielding. The stress will not increase and strain will be linear. Okay, but we idealize in stress strain curve. Now, what are the elastic analysis? In elastic analysis, material is in elastic state. Performance of structure under services load. Deformation increases with increasing load. As we increase the load, deformation is increasing. In plastic analysis, material is in plastic state. Performance of structure is under collapse load. Means we are going ultimate to the ultimate collapse load. And deformation increases without increase in loads. As we have seen, without increasing the stress value, strain is increasing. Now, some of the assumptions we take in plastic analysis are: plane section remains plastic in plane in plastic condition, and stress strain relation is identical both in compression and tension. That is normal. Like the stress, the compression and the tension for in flexural member will remain same. Now, how the section is yielded? We take m at any moment at any cross section increases gradually. If we increases load and the plastic limit point has been reached, when elastic limit reaches, then z is a section modulus, that is m by I is equal to sigma y by the basic equation of flexural member. Then elastic limit reach, then m is equal to sigma z here we have taken as elastic modulus I by y. When elastic इलास्टिक लिमिट रीच, yield stress reached. ठीक है, when movement is increased, yield spread into inner fiber, remaining portion still elastic. Finally, the entire cross section yielded. This means the cross section is yielding, still yielding. Yielding is done. Now the stress, how the stress strain stress graph is stress diagram is represented over here. At the point of yielding, it will be triangular at up, like triangular, and triangular at down, mean that one thing is showing compression, one thing showing tension. Now as the movement is increases, yes, stress is increases, the diagram tends to become rectangular from both the sides, from compression and tension side. This is showing that the stress is increasing, the strain is increasing, and the diagram becomes like we have seen here. The changes in stress distribution, first of all, sigma stress, we give an any sigma stress, then the sigma y stress come. This is the yielding stress at which the material has yielded. Then as we increase the moment, as we increase the stress distribution increases during yielding. Similarly, it will tend to become rectangular from both the side. This means it has yielded. Now the profile, we have taken inverted T section. First of all, we applied some kind of stress, then yield stress comes where the neutral axis, centroidal axis came. Then we gradually increase the stress value, the stress distribution increases and the strain value increases. Similarly, it becomes fully plastic at last diagram and became rectangular from both sides. Now, what is a plastic hinge? When the section is completely yielded, the section is fully plastic. The fully plastic section behaves as a hinge plastic hinge. Plastic hinge is defined as the yielded zone due to the bending in structure member at which large rotation can occur at a section at a constant plastic movement MP. That is, we have taken one MP, that is the plastic movement. Now this is small relationship between mechanical hinge and plastic hinge. Mechanical hinge we experience in reality. Plastic hinge we have given a concept. Basically they are both the same. When MP is equals to 0, there is resist zero moment. Mechanical hinge will resist zero moment. It will fail as fast as possible. It will resist a constant moment MP. Now M correspond to working movement corresponding to working load, My at yielding section, MP at when both the compression and tension side become rectangular, and that moment is known as MP. Like here the compression side and tension side is producing one couple moment which is known as MP, that is known as plastic movement. Plastic movement at which the entire section is under yield stress. Yield stress, movement at which entire section is at yield stress. Now here compression is equal to tension, so area at compression side into stress is equal to area at tension side, as we have seen in the assumption that compression and tension side will be both similar. So AC is equal to AT is equal to total, so total area is equals to A by 2, so compression is equal to tension is equals to A by 2 into sigma y. Now we are seeing the rectangular section both the sides. Now we have seen the compression force and tension force is A by 2 sigma y we have seen, and the lever arm from the neutral axis is YC and YT. We will add both, that will equal to ZP, that is plastic modulus, and this ZP by Z is the original lever arm. ZP, this YC plus YT is lever arm, that is equal to ZP whole lever arm, and ZP by Z should be greater than 1. This is a shape factor. This is a very important factor considered in plastic analysis. Means ZP by Z. ZP is the YC plus YT, that is the lever arm of compression and tension side, upon Z should be greater than 1, shape factor. Now we will see the shape factor of different figures. Like first we'll go for rectangular cross section. Z is equals to I by Y, section modulus I by Y. I is BD cube by 12, Y is equal to D by 2, it will equal to BD square by 6, and plastic modulus ZP we have seen A by 2 YC plus YT. YC we know D by 4, as we know here D by 4 and D by 4 BD square by 4, and we calculate ZP by Z, that is equal to 1.5. It is greater than 1, so it could be considered. Now circular cross section, similarly ZP is A by 2 YC plus YT, and similarly Z is equals to I by by and it will calculate shape factor that will equal to 0.1.7, which is great. Now for triangular section, similarly it will also come as 2.346. Now I section, we are also seeing I section also we are seeing s is equals to shape factor is equal to 1.132. In MP it yields greater MP as compared to oil, but shape factor is 1.132, and it is the most economical section to be used other than rectangular, circular and triangular. Now we'll be talking about load factor. Load factor is collapse load and working load. Collapse load means MP at where collapse happens, plastic moment, and working load we will all know M, that is sigma y upon zp. By z came we can consider as shape factor, sigma y by sigma into shape factor. ठीक है, लोड फैक्टर विल कैलकुलेट लोड फैक्टर MP we know sigma y BD square by 4. Rectangular cross section we are taking, MP will calculate. Similarly M is equal to sigma Z will also BD square by 6 will calculate shape factor. We know if we directly put it and we'll get the load factor as 2.25 for rectangular section. Now factor of safety, yield load work upon working load WY upon W, yield stress upon working stress sigma y by sigma, that is 1.5. It will come, as we all know, factor of safety. In elastic analysis, factor of safety is taken as, plastic analysis load factor is taken as. So load factor came 2.25. Here the load factor is important. It will be considered as load for the safety factor for plastic analysis. Mechanism of failure, statically determinate beam will collapse if one plastic hinge is developed. Consider a simply supported beam with constant cross section loaded with point P at midspan. If P increases until the plastic hinge is developed at the point, the maximum moment, an unstable structure will be created. Any further increase in load will cause collapse. So for a statically indeterminate beam to collapse, more than one plastic hinge should be developed. The plastic hinge will be act as a real hinge for further increase of load. As the load is increased, there is a redistribution of moment as the plastic hinge cannot carry any additional moment. Now beam mechanism, this is a mechanism will only consider a simple beam, a point load, a simply supported beam, point load acting at the center. This is a fixed beam. There are the different types of beam we are talking about: prop, cantilever, parallel. This is a sway mechanism, gable mechanism. Now there are some methods of plastic analysis: static method or equilibrium method, and kinematic method or mechanism method, virtual work method. The static method is known as a lower bound method. A load computed on the basis of first of an assumed equilibrium bending moment diagram in which the moments are not greater than MP is always less than to the true ultimate load. Similarly, kinematic method or virtual work method is the upper bound method. Collapse load WC and fully plastic moment is MP. Now we'll take a simple beam. In simple beam, a load is acting. MP is equals to WL by 4. It will be calculated with the virtual work method. We will be using virtual work method in our whole studies. That is the easiest method. Similarly, this is a virtual work method. If the WU is acting at the center, then the two theta from this side from one end and theta from second end will meet at the center, and it will correspond to 2 theta. And similarly, the internal work done and the external work done. Internal work done is MP moment due to plastic into 2 theta, which is acting 2 theta at the center. It is internal work done, and the external work done is WU, and the distance is L by 2 theta. WU external WU into L by 2 theta is equals to MP2 theta is equal to WU is equal to 4 MP by L. This correspondingly we'll find the fixed beam with UDL. Similarly, we'll get some value W, collapse load value 16 MP by L square. Similarly, fixed beam with point load will get 8 MP by L. Similarly, fixed with eccentric point will get 2 MP by L into A into B. A into B is a distance where the load is acting. Okay, virtual work 2 MP by L AB. Prop cantilever with point load at the mid span will get WU with as 6 MP by L. Propped cantilever with UDL will get WS 11.6.6.656 MP by L square. So this is all about the plastic analysis. Hope this could be a beneficial video for you. Thank you.